In this video, we will demonstrate the stop and start behavior of an ice stream according to a cycle outlined in Joffin and Alley, 2011. See the further readings link below to read more about theories behind ice stream start and stagnation after the video.
An ice stream is a fast-flowing ice channel bounded by slower ice on either side. When ice streams shut down and start up, the dominant heat transfer mechanisms switch between conduction and advection, as we characterized above.
When ice streams are moving, there is a thin film of water beneath the ice and on top of the bed, greatly helping the ice slide along.
As long as the ice is allowed to slide along the bed with lubrication, the ice stream flows much faster than the adjacent ice.
In this scenario, the heat transfer is advection dominated. This means that the ice stream is moving heat energy with its flow much faster than heat is conducted upward from the bed to the ice. As you'll remember from the heat transfer equations earlier, advection depends on velocity and the temperature gradient.
Let's think about temperature as it varies from the bed to the surface.
A simplified but useful way of thinking about this would be to say that temperature varies consistently throughout the ice column, so the relationship looks linear like this.
Now let's think about velocity as it varies from the bed to the surface.
We have sliding on the bed, but because frictional forces cause drag, basal velocity is smaller than that of the overlying ice.
Next, as the ice stream continues to flow, the ice thickness will start to thin, so we see the ice stream surface drop in elevation.
Because the ice stream thickness has decreased, pressure melting is not as strong at the bed, and the small film of water goes away.
Without the water helping the ice stream slide along, the ice body will freeze onto the bed and shut down. And by shut down, we mean it starts to move only as fast as the slower ice on either side.
In this thinned ice stream scenario, the temperature profile throughout the glacier changes slightly. Our new temperature curve, shown in purple, covers the same temperatures over a shorter ice thickness. On a standard graph with the independent variable on the x-axis and the dependent variable on the y-axis, this technically steepens the temperature gradient. However, we have flipped these axes here so that thickness, located on the y-axis, corresponds to our glacier sketches.
The velocity throughout the ice changes as well, because the sliding at the base has been greatly reduced, and so have the velocities throughout the rest of the ice.
With a slower moving ice stream, the system is now conduction dominated. As a reminder, conduction is controlled by thermal diffusivity and the thermal gradient.
After a while, ice thickness builds up again.
This thick blanket causes heat trapped at the bed to build up again.
The pressure increases from thickening and combines with trapped heat at the bed to eventually cause melting.
We have a new temperature profile at this point, shown here in blue, as the ice stream transitions back to its original thickness.
Soon, the film of water develops at the bed again, promoting sliding.
And voila! Green light for the ice stream.
At this point, with a fast-flowing ice stream, the dominant heat transfer mechanism switches back to advection, which, as a reminder, is dictated by velocity and the thermal gradient.
We must change our velocity profile to reflect basal sliding and adjust the overlying velocity to increase as well.
Our new temperature profile, shown in green, has adjusted to meet the original condition.
And we are back to the beginning of our cycle with the initial conditions we discussed.
Thanks for watching! Check out the links below for some interesting studies about ice stream behavior and examples of this happening in real life.